Figure below shows the cyclic thermodynamics process of an ideal gas that consists of two isochoric and two adiabatic processes. Prove that P1, P3 equal to P2, P4. The graph given in the questions is a P versus V graph, where the P is the pressure in Pascal and the V is the volume of the gas in the meter cubes. So that means these equations that the questions asked to prove P1 multiply P3 equal to P2 multiply P4. The P is referred to the pressure of the gas. The P1, P2, P3, P4 are the pressure for the four states of the gas shown in this diagram. So this one we call it as the state number 1 with the pressure P1. This is the state number 2 with the pressure P2. Similarly, we have the state 3 with the pressure P3 and the state 4 with the pressure P4. The two isochoric processes refer to the process happens between the state 1 and state 2 and state 3 and state 4. But the directions of the process is not mentioned. So whether the isochoric is happen from the state 1 to state 2 or state 2 to state 3, it is not important because the questions never mention about it. And similarly, between state 3 and state 4, whether the isochoric process is happen from the state 3 to state 4 or state 4 to state 3, it is not important because the questions never provide any information about it. The two adiabatic processes is referred to the process happens between the state number 2 and state number 3. And also the state number 1 and state number 4. Again, the directions of the adiabatics is not mentioned in the equations. So either it is the adiabatic expansions from the state 2 to state 3 or adiabatic compressions from the state 3 to state 2. It is not important. And also, the adiabatic happens between state 1 and state 4, whether it is adiabatic expansions or adiabatic compressions. It is not important in these equations. Between state 1 and state 4, no matter it is adiabatic compressions or adiabatic expansions, we can write down the equations to relate the products of the P and the V for the two states through these equations because this equation is valid for adiabatic process. It is valid both for compressions or expansions. So now, even though we do not know what is the directions of the adiabatic process, whether it is expansion or compressions, it doesn't matter because we can still writing down these equations for the state 1 and state 4, which is valid for adiabatic process. Gamma is the specific heat ratios for the gas. And in this question also, we do not know what is the structures of the gas. So the value of the gamma also is we do not know. So never mind, we just leave it as the gamma. Therefore, now we have this P1 over P4 equal to the V4 over V1 to the power of the gamma. So we name this as equations number 1. Follow the same idea and the steps. Now we can write down these equations for the state 2 and state 3 that undergoes the adiabatic process. And now for this case, we have the ratio between the P3 and P2 equal to the V2 over V3 to the power of gamma. and we name this as the equations number 2. Now we use the equation number 1 multiply with equation number 2. Then at the left hand side of the equality sign, we'll have P1 over P4 times the P3 over P2. Now at the right hand side of the equality sign for these two equations, we will have V4 V1 to the power of gamma multiply with V2 over V3 to the power of gamma. But since these two indexes for the gamma is the same, so we can factorize it, and then we'll get V4 V2 over V1 V3. But now the things in the bracket is equal to 1 because these volumes for the state 1 and the volumes for the state 2, they are the same. In the process that happens between state 1 and state 2, it is the isochoric process. So that means we know that the volume of state 1 and state 2 are the same. So that means 1 and 2, V1 and V2, we can cancel out. Similarly, between state 3 and state 4, since between them the process are the isochoric process, so we know that V3, the V3 and V4 are the same. Therefore, we can also cancel out. So the things in the bracket now will become 1 to the power of gamma. So no matter what is the value of the gamma, then we will get it is equal to 1. Now we can bring the P4 and P2 from the denominators of the terms at the left hand side of equality sign to the right. And then we will get P1, P3 equal to P2, P4. This is the things that we want to prove. There are two important points need to be emphasized. The first one is about the gamma. Since the thing in the bracket is reduced to 1, so that means no matter what value of the gamma we take, the answer is always equal to 1. So that means this relationship is valid for all types of the gas, no matter it is monoatomic, diatomic, or the polyatomic gas. The second important point is also related to the gamma value. Because the final answer that we obtain here, which is these two products equal to 1, is independence of the gamma value. So that means if we replace in the first line and the third line, the gamma value, if we take 1 and reduce these two formula to the Boyle's law, then the final answer that we obtain will be still the same. So that means, although the questions ask us to consider two adiabatic process, but if we change these two adiabatic process to the isothermal process to make this gamma value equal to 1, we will still able to get the same answer. So that means this result that we obtained is valid if this cyclic process is composed of two isochoric and two adiabatic process, also valid for the cyclic process that consists of two isochoric and two isothermal processes.